Good morning, guys. Today let's look at the second part of our lesson on binomial geometric random variables by talking about geometric random variables. So here's today's question. Let's say that Bill goes into a shooting slump. So instead of being an 80% free throw shooter, he just starts missing. So let's say that he goes into a shooting slump. How many attempts will it take before he finally makes a shot? All right, so that's a very, very different question. How many attempts will he make before he finally makes a shot is very different than how many shots will he make. That was the question we asked in the last lesson, the last part one of this video. How many shots will he make, or how many will he make out of a certain number of shots? That's what we decided was a binomial situation. Fixed number of attempts. We had it being a yes or no situation. Did he make it or did he miss it? He had the same probability of success on every case, or every attempt, and missing one or making one didn't change that probability. So it was binomial. This one's different because this is what we call a geometric question. So in a geometric, how many attempts will it take before he finally makes a shot? That's the key. Before success. That's what makes something geometric. Number of attempts, number of trials before success. So instead of it being binary, independent, fixed number of trials, fixed success, it's binary, independent, and then variable number of trials. So that's what we're looking at in this case. So the number of trials until success is the variable. So in a geometric setting, you know I'm going to attempt this out of this many times. And in a geometric, you're asking how many times. So it's kind of almost an inverse type situation. One, we're asking for the number of trials. The other one, we're asking for the number of successes within those trials. So in this problem, it's how many attempts until he makes one. So it's a little bit, I don't know, I always think this one's kind of a more difficult question to kind of think about from a probability standpoint. But calculation-wise, it's a whole lot easier, and you'll see why here in a second. But it's still pretty much the same general idea, which I guess is why a lot of students will get these confused, because we're dealing with something that's binary, dealing with something where one trial, one attempt should be independent of the others. We have that constant rate of success. But now the number of trials varies. So our acronym for a geometric setting is BITS instead of BINS. And so we don't have a fixed number of trials, we have a varying number of trials. Well, how do we go through and calculate this? So we see this formula right here. The probability that y is equal to k. The probability, what does that mean? Probability that y is equal to k. That just means the probability that our first success is on the K trial. So the probability that he misses until his fifth shot, probability he misses until his third shot, probability he misses until his 20th shot. That's what we're talking about. So that's what the K represents in this case, the position of that first success. So if we're going through calculating, we know that 1 minus p, that's not p, so that's our probability of failure. Where p is probability of success. Now, how many times are we looking for him to be successful? Until he finally makes a shot. So we stop counting as soon as he has that one success. So that's the number of successes. So if he tries and tries and tries and fails and fails and fails until he succeeds, then k minus 1 represents the number of failures. So it's really the same as our binomial probability formula. Take the number of failures raised, or sorry, probability of failure raised to the number of failures, probability of success raised to the number of successes. The only things that have changed is the number of successes is always going to be 1. Okay? Always going to be 1. The other thing is, notice what's missing. We don't have that binomial coefficient in the front this time. Because before we could rearrange all the different ways to get 2 made shots or 3 made shots out of the 7 attempts. There's only one way this can happen. It's fail, 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 then make 1. So it's always going to be the exact same order. So let's go through and work an example. So let's do the probability that y equals 4. Probability that he makes it on his 4th shot. So what does it mean to make it on his 4th shot? That means he missed the first, and missed the second, and missed the third, and he makes the 4th. Well, that's nice because we know what to do with and. And with probabilities just means multiply. So what was the probability on the first shot that he was going to miss it? Well, he's an 80% free throw shooter. If you remember about Bill, 80% free throw shooter, so he's a 20% misser. So 0.20 on the first, 0.20 to miss the second, 0.20 to miss the third, and 0.80, 80% chance that he makes it for that 4th. Remember, they're independent. That was a key feature right there. You have the same probability of success on every single one of them because they're independent. So what do we end up with? 0.2 to the third times 0.8 to the first. Probability of failure with an E. Probability of failure raised to the number of failures, missed it 3 times. Probability of success raised to the number of successes. So when we go through and do the calculations on that, we get 0.0064. So a little bit more than 0.5% that it takes him all the way to 4 shots before he makes one, if he's an 80% free throw shooter. All right, so that's the by hand way we can calculate geometric probability. So it's very similar to binomial probability. You just have only one way, so you don't have the binomial coefficient on the front, and because the number of trials is what varies in this case. Now let's work through a few examples. Here I want you to write and sketch a histogram of the probability distribution for the number of attempts before Bill makes a free throw. We're only going to look at the first 7 attempts, because technically this could be an infinite series, right? He could potentially never make a shot again. He can miss every single one of them. So let's look at the first one here. Before we fill in here, we got to do one of them. What's the probability that it takes exactly 3 attempts for Bill to make his first shot? I want you guys to pause, think about how we just did it by hand. Pause the video, take about 10 seconds or so. Calculate the probability that it takes him exactly 3 attempts for him to make his first shot. And I'll wait right here. All right, so let's go through it. So the probability that y, I'm just using y as my geometric variable here, is equal to 3 would be, well, what does 3 make it on the third looks like? That means he missed on the first 2 and he made it on the third one. Okay? So probability that he misses on the first 2, makes it on the third one, and you get 0.032. All right, 3 decimal places off of 32. Yeah. Okay. Now that's the by hand way. Let's look at how we can do this on the calculator. If we'll look right here, we're doing the exact same thing as we did in geometric or in binomials. We're in the distribution menu, so second vars. If I want it to be an exact number, an exact position, exactly the third spot, I'm going to use my PDF situation. Difference is I don't have to do NPK because we don't know the number of trials. That's what we're solving for, is the number of trials until success. So I just need my probability and my position of that first success. So that's what K represents. So K is the position of first success. Position of first success, and then P is probability of success. So PDF tells us the exact number if we have inequalities, just like before. Okay, but instead of using binomial CDF, we're using geometric CDF. And so we get this situation right here, less than or equal to. It's a less than or equal to function, so we just type in K. If I want just less than, then I need to reduce my K by 1, my position by 1. If I want greater than, remember anything greater than, you got to do 1 minus, because if you want right side stuff, you got to subtract the left side stuff from 1. So 1 minus, whether it being equal to K, or letting it be equal to K. And then if I want greater than or equal to K, that means I do not want K minus 1. So 1 minus K minus 1. So it's the exact same kind of thought process on how to adjust your values as we used for binomials, because it's still a less than or equal to function. Should have noticed here that these graphs look a little bit different than the graphs that we used on the binomial. So let's go through and work this example. I want you guys to fill in the table here. So calculate the probability for each of these values. So probably that he makes it on his first, or his second, or his third, and so on. So calculate those probabilities, and then we'll put it into this graph up here, and we'll talk about how geometric graphs and binomial graphs are a little bit different. Show you guys something that looks like this. All right, as we can see, our probabilities, 0.8, 0.16, 0.032, 0.0064, 0.000128, 0.0000256, and then 0.0000512. And then this is what our histogram ends up looking like right here. A couple things. I think you guys see the pattern right there, and that should be an intuitive thing, because all that happens is whenever you make another miss, add another trial on there, you're just multiplying by 0.2 again in this specific case. So that's why the decimal moves one place and we double up too. So hopefully you were able to identify a pattern and save yourself a little bit of time. It's the same idea right here too. So we start out with an 80%. Now that should be, again, an intuitive type thing. He's an 80% free throw shooter. So there's an 80% chance that he's going to make it on any one shot. So that should be 80% on his first shot. Then what happens is it went from 80% all the way down here to 16% because that 20% chance. So it reduced by a fifth. And that's what's happening. It's reducing by a fifth every single time. Now this is different than our binomial graph that we saw in the last video, where everything was clustered around 5, 6, 7 attempts. Now we had found the expected value was 5.6 attempts for Bill out of his 7 attempts. So that's why that peak is around 5.6. It's the most likely outcome is for him to make somewhere between 5 and 6 if he's trying out 7. Most likely outcomes for him to make 80%. This is different because it's always going to have, this is always going to be a right skew distribution. On binomials, if your probability is less than a half, you're going to have a right skew distribution, but if it's greater than half, you're going to left skew distribution. Geometrics are 100% right skew, and it's because of the way they're calculated. Because your highest probability is being successful on your first try, even if it's a small chance, right? Because what you're doing is you're taking a decimal value and multiplying it by another decimal value right there. So it automatically has to get smaller. When I take a number and multiply it by a number smaller than 1, it's going to get smaller. So the fact that I'm multiplying 2 of those decimals together, we're going to automatically be smaller and smaller and smaller every step of the way. So you always get this right skew distribution. That doesn't happen with binomials because binomials we're multiplying and getting a lot of small numbers. We're also adding a bunch of them up. Sometimes we're adding more than others together. So that's what that binomial coefficient does. So that's why your binomial can take on any shape, and we know that when we get really, really large numbers of trials, then that shape becomes normally distributed. Geometrics don't do that. Geometrics will always have this right skewed shape because the most likely outcome, or the highest probability outcome, is always that first success on the first attempt. All right, I want you guys to take a minute. Okay, so using the calculator features that we talked about right here, so second vars going into your distribution menu, grab a geometric CDF, probability that he has at most 5 successes. So the probability that y is at most, meaning less than or equal to 5 successes. We could do it by adding up right here, okay? Or we can go in and do our binomial or geometric CDF. So I'll give you guys a second to kind of work through that. Let's put it back over there so you can kind of see the formula. So less than or equal to 5, calculate the probability that it takes him less than or equal to 5 shots to finally make 1. And I'll wait right here. All right, guys, hopefully you recognize that less than or equal to is just the normal geometric CDF function. So when I go geometric CDF, my P is my probability of success, that's 8. My probability, or my successful trial is the 5th trial. So it's going to calculate from 5 all the way back to making it on the 1. Okay. Same thing I could have got if I'd have just added up all of that stuff right there. So all of these probabilities added up together, all of that would give us the same thing the calculator is going to give us right here. But when you threw that in the calculator, you should have got like 99.7% or 0.9997. So there's almost 100% chance that it's going to take him less than 5 attempts to make one if he truly is an 80% free throw shooter. Possible that it takes more, right? There's always that chance when we're doing a random or chance process, but this is possible. All right, so that's how we do calculations with geometric. Let's talk about just characteristics of the geometric random variable. So it is quantitative, so we will have a mean and standard deviation, and they're calculatable. So we can get these means and standard deviation. Well, how do we get this? Because this one's not as intuitive as our binomial. Binomial expected value was number of successes times the probability of successes. That's what we'd expect to happen. In this case, our expected value, our mean, is going to be 1 over the probability of success. Why is it 1 over probability of success? Well, let's take a step back and go to our binomial again. So the expected for a binomial, right, is going to be n times p, right? Well, in this case, n is the number of trials. Well, that's our variable. That's what we're trying to figure out. So that is our expected value in this case. P is still the probability of success. So if I go with my expected geometric value, expected number of trials until I make 1, that's my variable. This has got to be 1, right? Because success is that we're going to make a shot, right? So we are, at some point, after a certain number of trials, we should make that 1 shot. So we're only wanting 1 success out of we don't know how many trials. So it's just taking our binomial, because it was a binary setting, our binomial expected value formula, or binomial mean, and we're just adjusting it based on what we don't know. So if I now take this equation and I just solve for the expected value of the geometric, we just divide both sides by p, so we get the expected geometric is 1 over p. That's where that formula comes from. It's just a manipulation of the binomial. So let's go in and do our calculation. Let's see, so it's 1 over probability of success, so 1 over 0.8, which equals 1.25. Attempts before he makes a shot. So that's how we would interpret it. after many sets of shots, or attempted shots, yes, after many sets of shots, we expect Bill to let's say we expect the number of shots for Bill to make one to approach 1.25. So if we just had Bill shoot until he makes one and we recorded how many shots it was, and then shoot some more until he makes one, record how many shots that was, and then shoot some more until he makes one, and then record how many shots that was. Every time he makes one, that's one simulation, so to speak, or one set of attempts, and then we do that again until he makes one. When we take all of those number of attempts and average them together, it's going to approach 1.25. That's what that expected value is telling. You could also maybe think of it as what's the expected number of consecutive misses that he could have, right? Because we would expect him to make it once out of every 1.25 shots or so. I guess that is what we're saying. We expect him to make it once out of every 1.25 attempts. Once out of, and that's kind of what that formula ends up giving us. Once out of every 1.25 attempts. All right, now let's talk standard deviation. Now, the standard deviation looks like it's its own weird little formula, but it's actually kind of similar to our binomial. Remember, binomial standard deviation was square root of n times p times 1 minus p. So you kind of got your expected value being related to square root of 1 minus p. Well, this is sort of what we have. It's not identical, but it's very similar to it. Because if I think of this as square root of np times square root of 1 minus p for a binomial, well, this is almost like 1 over p times square root of 1 minus p. So this is almost like expected value times square root of 1 minus p. So very, very similar to that relationship with the binomials. Not the exact same, but it's very similar to it. But really it comes down to square root of failure divided by success. Square root of failure divided by success. So if we go through into our calculations, failure was 20% of the time, success was 80% of the time. So square root of 0.2 over 0.8 is equal to 0.559. 0.559. And that means the same thing standard deviation always means. That means if we expect him to make it 1 for every 1.25 shots, that means we expect that for many, many trials, that number of attempts till make is going to typically vary by about 0.5 shots. So some trials will take a few more attempts, some will take a few less attempts. But they'll typically vary from that 1.25 by about 0.5 attempts. All right, that's it for geometric probability and binomial probability we talked about in part 1. Make sure we kind of get these little formulas down. Geometric is nice to know, nice to work with, but binomial is very, very important for what we do going forward. So make sure you've got all of that stuff down, especially those conditions and those calculations there at the end. So that's it, and I will see you in class tomorrow, guys.